Ladies and gentlemen, it's 5 p.m. I'm very much honored to welcome the speaker of today, Professor Ivona Brandic, who is known for her work on energy efficient IT, but going further in the area of edge AI, using AI for climate change, but at the same time also talking about the kind of the bad side of AI. And I think also her title of today shows that she starts out with sustainable IT, but goes into IT for a sustainable world. Thank you that you are all here. Thank you that you are here, Ivona, and it's your floor.
Hello, everyone. Hello, Gerti. Thank you very much for the introduction. Yes, I'm very happy to be part of this lecture series and also to tell you about some fundamental research about sustainable IT and also how can we use IT to build a better or more sustainable world. And I would like to start with basics, what happened in the last years and where we are experiencing differences in our infrastructures. And what happened in the last couple of decades is that we experience rise of computational power and availability of computational power that is fundamentally changing the way how we work, how we think, and how we interact with our environment, I would say. What we in particular had in the past is the power of simulations, where we can simulate real systems, for example, using finite element simulations. I don't have to crash two cars. I can simulate car crash and repeat it and repeat multiple times, so it's more cost efficient. I can do much more than I can do with the real system. If we repeat simulations multiple times and try to fine-tune certain parameters, then we talk about optimization, for example, airflow optimization. And today I don't also have to talk much about the power of analytics, AI, large language models, and all the changes and developments that we have experienced in the past couple of years and that we are still experiencing nowadays. However, all those developments, they lead to some practical limitations in computer science in particular. And if you look at this picture, what you can see here is the development of the microprocessors in the last 42 years. And what you can see here on the X, you can see the time, and here you can see the number of processors. And if you look into this picture, there are certain observations that we can do here. You can see the exponential growth of the number of transistors. So this is the logarithmic scale. And on the other hand, we see the stagnations of the single thread performance. Since 2006, we basically did not have significant improvement in frequency. The only way to keep our computers being able to process more data and to be faster is to build more logical cores. And here we started with dual cores, quad cores, and so on. So we have to parallelize workload. And this leads also to different other problems because the density of our computers and the density is getting much, much higher. So the heat is developing. So if we keep up miniaturizing our computers, they are basically going to melt. So we are having some practical limitations in our processors, and this is creating serious issues currently with this rise of AI. On the other hand, if you look at this picture, it shows clearly the power of AI today. Maybe you already know it. But if you look also clearly to this picture, you can also see the limitations of AI. AI basically cannot count till 10 or 5, right? It has some serious limitations. Also, the generative AI is getting better and better. I mean, this picture is, I think, also old, like 1 or 2 years, but it shows also some limitations. Nevertheless, if we talk about the power of AI and generative AI, we have also to consider the usage of resources, because all IT equipment, all AI tools need resources. And here you can see comparison of generative AI compared with some everyday activities of human persons. For example, you can see here different activities, and here the CO2 emissions or equivalents of the CO2 emissions. You can see here the CO2 footprint of air travel from San Francisco to New York, CO2 footprint of a human life, or 1 year in a human life, and then of an American life. You can see the CO2 footprint of a car during a lifetime, training one deep learning model, and a transformer, right? So you can see here, although there are different methods, there are different tools to assess these numbers, I don't say that the numbers are exact, but I think the relation is still very, very valid, and should show you the relation between everyday activities and the order of magnitudes that we might have here. On this picture, you can also see the assessment of the CO2 footprint or resource consumption of generative AI. On the left-hand side, it's our whiteboard where we put all the data. On the right-hand side, you can see what my colleagues created, nice pictures, and nice visualization, also with some AI tools. As already mentioned in the introduction of this lecture, if I ask ChatGPT approximately 5 to 50 prompts, depending on the location where I am on this world, I might consume up to half a liter of water. If we switch Google search from index-based search to LLM-based search, we are going to use 20 times more resources, for example, electricity, because it's going to be much more expensive. If we generate text to image and perform around 1,000 inferences for the same amount of energy, we can switch on our dishwasher, in Europe at least, with our carbon intensity and our electrical grid. And if we generate 1-minute video, for example, with Midjourney, for the same amount of energy, we can play a PlayStation, I don't know, the whole weekend. So this is just to give you an idea about the order of magnitude we are talking here, and about the resources that we need here. So what can we do here? Well, in research, we have already multiple approaches to counteract to this development. And one branch of computer science that I'm in particular working on is called computational sustainability. And it deals with multiple dimensions of sustainability where IT resources and IT tools are involved. So first aspect is to assess, to measure, to visualize, and to counteract to the resource usage of IT tools. It can be hardware, it can be software, right, to make it more efficient, to make it more sustainable. On the other hand, we have also to counteract to the IT's impact to the nature, CO2 footprint, on the one hand. On the other hand, if we want to protect our nature, if we want to protect from flooding, if we want to protect from fire, we need IT, right? We need IT to protect our nature from the impact of the climate change, for example. And everywhere we have humans, right? We need humans to run IT, to operate IT. We need humans that interact with the nature. So here are the actors that we have in this concept of computational sustainability. On the other hand, we have different methods that we can use to increase the efficiency of IT, for example, or to develop tools and methods to combat climate change, right? Or to improve impact of IT to our nature. And we have, I would say, in a coarse-grained manner, three basic methods. The first one is disruptive, where we take disruptive technologies that just change the way how we interact with the environment or how we process information. Can someone of you tell me some disruptive technology we had in computer science? You can write in chat or you can just speak if you like. What would you consider as disruptive in computer science? For example, internet. Internet was a totally disruptive technology, invention of transistors, AI. I would also say invention of smartphone. Yeah. And this is absolutely correct, what you have written. Well, invention of disruptive technologies happens every now and then, so it doesn't happen that often. The other method that we can use is the trade-off, right? Trade-off means we give up something, for example, accuracy of our software for the sake of better efficiency or for the sake of sustainability, right? And there is a third method. The third method is to convince people, to convince humans to change the behavior, for example, to use less computers or to use less smartphones, right? Which is a bit difficult on such a scale. If I tell you, please stop using your computers or please stop using your smartphones, no one is going to do that. So this have to happen on a completely another level. So we need guidelines, we need policies. It has to happen from the politics, organizing how the people are using software, how the people are using hardware, where is the electricity coming from, and so on. So this is super difficult to be implemented. And I also want to tell you about some of the projects in my group that we are dealing with. So if you look on this landscape of computational sustainability with actors and with methods, so projects that I'm working on in my group are everywhere. We have projects where we develop digital twins of watersheds in order to predict pollutions if they happen. We develop virtual shepherds for the Austrian farmers and facilitate automation or digitalization of the farmers and the environment that they have, so they don't have to be in person, for example, at pastures, but they can visualize using IT tools what is going on. We are working also on some disruptive methods, for example, by including quantum computers in high-performance computing environment when necessary and when useful, also for the sake of sustainability. And we are developing different trade-off mechanisms, for example, transprecise edge, where we develop formal methods to prove the transprecision, means if you give up certain dimension to make sure and give certain guarantees about the behavior of the software. And also we develop code offloading mechanisms also for the sustainability issues. The most difficult method, as I told you, is behavior change. So I cannot change the law, I cannot change the policies, but what I can do, I can educate. That's my job. So I'm educator. And for example, there is also one project with Austrian Academy of Sciences where we are recording YouTube videos for teenagers and explaining them the increasing energy consumption of IT infrastructures. And Here you can see also some snapshots from the videos. It's called FACT series, where different researchers explain different concepts in science, and where we try to educate students and teenagers about the state of the art that we have currently in science. And there are different types of videos. We are on YouTube, we are on TikTok, and so on. And there is also another example that I want to show you, which is from Ars Electronica Festival that was this September, where Yasmo presented a rap song about AI, also speaking about energy consumption of AI in a rap song, right? So what I'm trying to tell you, we have to use the channels that are available. We have to use tools that are available to reach the people that are on different ages, and to educate about the impact of AI to our environment. And I mean, here is just to show you the song, and here is just one example. Hey, AI, you are pretty bright with the data that we feed you. Nothing's going to break your stride. But don't worry, we don't need your help for every single starter. Does a conversation with you cost us half a liter water? Well, I think a nice example how we can educate using different tools, different communication channels that are maybe adequate for these different groups of persons. Okay, if there are any questions, please feel free to write in chat. I'm from time to time trying to check if there are any questions. Okay, now, as the second part of my presentation, I would like to present you some methods for computational sustainability, and I'm going to present first some trade-off methods in computational sustainability. And what I have created here, or what you see here, is a very powerful tool in computational sustainability, which is called virtual machine. What I've created here is a virtual machine. It's a computer running on another computer. I can create the second one. I can create the third one, fourth one. And what I'm doing here, I'm applying a very powerful method in computer science called virtualization, where we decouple data and computation from the physical entities, right? And this is basically a very powerful tool. And if I do that, what I've done on the small scale, on my desktop computer, on my laptop, if I do that on a large scale with multiple physical data centers, this is what we call cloud computing. So what I have done here, I have here 3 geographically distributed data centers. We have a layer of physical machines, then we have a layer of virtual machines. And now what I can do, I can move now for different reasons. I can move data, I can move computation between geographically distributed data centers. And one of the reasons to move computation and data between geographically distributed data centers is also for sustainability issues. I can move from one data center to another because I have at a certain location cheaper energy, or I have greener energy. And cloud computing was one very fundamental method, or is still one very fundamental method to build economic and ecological data center solutions, using also some trade-off mechanisms. And what I have shown you here on this, I would say, rather small example, you can do the same also on a very large scale. And this is example from our lecture on data-intensive computing. This is held together with me and Shashi Ilaga and Anna Radovanovic from Google. And one part of this lecture is exactly about carbon-aware computing in Google, at Google and beyond. And they are using very similar approach what I have shown you with geographical distribution of virtual machines. It is called workload shift in space and time. So if you look at this diagram here, you have here your workload during the day. And here you have the intensity of your workload in CPU numbers, right? You can see here we have inflexible workload, which has to be executed immediately. So you cannot shift in space and time. But there is, for example, during the high carbon intensity, this is around noon, we have very high energy prices. We have very carbon intense electricity. During the midday, there is certain workload that can be shifted to the next day. This can be, for example, if we follow previous slides, this can be, for example, model building of some, I don't know, large language models, which is not crucial and not super critical, right? So you can postpone it for a half a day. There are many other tasks that can be postponed for a half a day. So what is done here? This in non-critical workload is postponed to the midnight, right? And during the midnight, we have low carbon intensity. That means we have more sustainable execution of our workload. And this is just an example. Here we have the shift in space, right? But you can also, this is shift in time, but you can also do shift in space, as I have shown on my previous slide, by moving virtual machines between geographically distributed data centers. So if I may ask you now, what do you think are the trade-off dimensions here? What do I trade off here? What do I lose if I use this technique to shift workload in space and time? Any idea? What do I trade? Exactly. Speed, right. Well, more technically, latency means the applications are finished a little bit later. But if execution of the applications is finished a little bit later, but if I don't care whether my model training is finished half a day later, then that's fine. This trade-off is fine. Okay, excellent example. Good. So let's go on. This is the first method that we have as a trade-off, right? So let's look into the second method that we have as a trade-off. And the second method is utilization of symbolic data. We have symbols everywhere in computer science, and this is just an example that I'm showing you here, where we have object detection. So if I'm doing smart cities and if I'm doing surveillance in a smart city, so I'm probably not going to store raw data here like this picture. I'm going to detect the objects, for example, cars, persons, bicycle, as soon as possible, and then process the symbolic data, no matter what I'm doing. For example, if I'm counting cars or if I'm counting pedestrians in a certain area. And this is a very, very powerful method also to increase sustainability in our systems. And I'm going to show you how we can utilize symbolic data representation. Symbolic detection of object is basically done today everywhere. Here is an example. Here is an example from one of our projects that we had with City of Vienna, where we had a very difficult crossing in Vienna. You can see here is the bus stop. Here is the bicycle driver, and here is the car that has the right turn, right? So what can happen is that this car driver just don't see the bicycle driver, and then everyone is doing right, but very bad accident can happen, right? And the question is, can we solve this situation with state-of-the-art methods that we have in computer science? And we said, yes, we can. So what we developed intelligent traffic light here. So with this intelligent traffic light that is installed on this traffic light, we have a bird view, right? So we see objects that car driver cannot see. And this camera is trained. We use convolutional networks here. So we can detect objects like bicycle drivers, kids, pets, everything what is, you can find on the street. These video frames are sent to the edge node, which is installed also in this traffic light. So it's a really small computer, Raspberry Pi. And this edge processing unit detects the objects. And the detected objects are sent to the 5G antenna, which is seen here. So this is our experimental setup. It is a real crossing in Vienna. So here is the 5G antenna. And the 5G antenna sends then the detected objects to all cars in this vicinity. So you see the screen of the drivers in a car, I think this car or that car, and you can see, okay, there are pedestrians on this street that you maybe don't see, right? And with this project, we won the 5G Vienna use case challenge. We showed and demonstrated how we can use 5G in order to save human lives, which is, I think, the purest form of sustainability, saving someone else's life, right? But this project opened so many questions and opened so many research directions in my group. And one of them was, maybe we don't have just to look for symbols on the street or on the traffic light. Maybe we can look for symbols in arbitrary streams of data, because sometimes transferring symbols instead of raw data is cheaper, is more efficient, is more sustainable, right? And this is just an example to show you how symbolic data representation can be applied in time series of data. We have here numerical data, where you try to find polygonal chain approximation. So you see here 250 points of data, right? And what we try to find here, we try to approximate here pieces of data with lines, right? With polygonal chain, we find the begin and end, and we try to find the increment, right? And if you look here at this clustering example, where we have the length of the polygonal chain and the increment, you can easily see that around the cluster centers, the pieces are very similar. For example, if you look here at this yellow part, where we have 4, 6, and 1, and if you look at 4, 6, and 1 are basically very, very similar, but they have just a different start and end point. And the idea here is to, for example, symbolize similar pieces of data here. And just a rationale of this idea is it is cheaper or easier to transfer A, B, B, A, C, A, B if we symbolize this data instead of 250 values of numerical data, right? So this is the idea. And for this idea, we got also, or one of my master student got JS Appreciation Prize at Europar, which is one of the oldest conferences on parallel data processing. And this method opened also so many questions. And what I also would like to ask you here, what is the dimension here that we trade off if we symbolize the data? Any idea? Let me see, what do you have in chat? Precision, accuracy, absolutely. We have to give up some accuracy, right? But in many cases, let's go back to this example with car detection. If I detect, I don't know, 95% of the cars, but I use just half of the energy for my software, I think the trade-off is still good, right? Sometimes not that accurate solution is still good solution in many cases, but you save a lot of energy, and that's all about here, right? This is the typical outcome of the trade-off methodologies. And what I also want to tell you, we have follow-up lecture, which is going to be called Introduction to Computational Sustainability. So if you are in particular interested in these trade-off methods that we are using here, this lecture is going to start next year, I think in winter term 2025. Today we have it, but it's called AI/ML in the Era of Climate Change. We are going to change that lecture to Introduction to Computational Sustainability, because this is now the subject of the lecture. And we have two parts. In the first part, we measure, assess, visualize the impact of sustainability by AI models, hardware advancement, energy challenge of AI models, cost of training and inference, large language models and their energy consumption. And then in the second part, we have AI for sustainability, using AI to combat climate change issues, not only throwing AI to all the problems that we have in climate change, because you don't get solution, you get even worse problems if you just throw AI. You have to use or develop methods to do that. One of them is, for example, this trade-off method, or utilization of symbolic data representation, or transferring workload in space and time. Okay, so if you're interested to learn more about these methods, feel free, and you are more than welcome to attend this lecture. Now, I would like to give you some ideas about the disruptive methods that we might have in computer science. And one of the, I would say, most disruptive methods that we have nowadays is the utilization of non-von Neumann architectures. So our data volumes are growing faster than the processing power. That's also what I have shown you in one of my first slides. And all the laws that I have learned is the students like Moore's law, that our computational power is increasing every 18 months. They don't hold anymore. So we have to look for alternatives. And one of the alternatives is, beyond von Neumann architecture. So scientists look today into neuromorphic computing, into quantum computing, right? And there is also another change that is happening in computer science. In the past couple of decades, we had generalized architectures. So we try to execute all kinds of workload on a very generalized architectures. Now, we are going into opposite direction, having and developing hyper-heterogeneous architectures. If you look at this slide, you can see here the requested computational precision, for example, computation of very low precision, but also computation of very high precision. For example, if I'm generating random numbers, they do not have to be very accurate. I know if it's a long discussion, but let's assume they don't have to be accurate. But if I'm solving linear and partial differential equations, they have to be accurate. We have different computational complexity here, and we have also different data access rate. For example, in deep learning training, we have high data access rate. In random number generation, we have low data access rate, right? So the idea here is now to have different architectures for different type of computational problems. For example, to use approximate computing, to use neuromorphic computing when possible. And as if this is a computing that mimic human brain, or to use quantum computing that benefits from the atomic structures, right, of and atoms. And as a result of this development, in the past, the precious computational cycles were spent on computation, but now more time is spent on communication between those heterogeneous architectures, right? So this is the development that we have now. I would like to give you a brief overview of how quantum computing can be also used to increase sustainability. So what we have in quantum computing, we are talking here beyond 0 and 1s. So we are talking about qubits and quantum bits, which work with the with this Bloch sphere and characteristics of an atom. And you don't have to be expert to understand what we can do with this representation, right? So we don't have 0 or 1. The qubit is in a superposition, in a complex amplitude. Once you measure it, it collapses in the bases that are 0 and 1, right? And if you look at this picture, what could we naturally represent here? Well, some form of native computation. So if you want to represent, for example, molecules and do some operation on the molecules, this is the right representation. This is the native form of computation. So native 3D modeling of scientific applications, for example, representation of molecules in scientific computing. And there are already algorithms that can be applied here in order to manipulate also such representation. However, the problem is today that currently only current quantum systems can only be used by quantum researchers, right? So there is the problem with the interfaces and also the interconnection with the remaining world, right? That is not quantum. And there are still several reasons or many reasons why we should use this form of computation. And this is this power of space efficiency. It is called space efficiency. Every time you add a qubit, you double your possible outcomes. With 20 qubits, there are million possible outcomes. With 100 qubits, you have more possibilities than there are bits in the hard drives in the world. And with 300 qubits, that's more possibilities than there are particles in the universe. So if we represent the energy configuration of a single coffee molecule at a single instant, it requires approximately 10 to the power of 48 bits in a classical computer. It can be done using 160 logical qubits on quantum machine. And this is just for visualization. So there are certain areas, in particular scientific applications, where we have to model molecules or behavior of molecules over time that can be executed much more efficiently on such machines. And it is not a coincidence that I'm also working on this topic, but in Austria we have a huge number of research institutions who are doing world-class research in quantum computing, so where you can easily get in contact and talk to researchers in this area. And we have also quite a few startups that are internationally very successful. For example, QT Labs, they sell satellites. So if you want to develop quantum communication, you need this type of satellites. And AQT, Alpine Quantum Technologies, they are developing quantum computers that you can take and put into the rack of your data center, right? Ion trap machines. And the quantum computing allows us certain speed up that is beyond the classical algorithms. For example, if we talk about Grover's algorithm, which is used for unstructured search, or if we talk about Shor's algorithm, which is used for finding the prime factors in the integer, where we have excellent speed ups. Currently, the research is focused also on quantum machine learning, where we try to find forms for Bayesian inference, support vector machines, and reinforcement learning. But in reality, there are a lot of problems. First of all, there is lack of standardization. So I have here pictures of 3 different technologies that can be used today for quantum computing. We have D-waves, we have trapped ion machines, we have superconducting machines, plus every machine, every quantum machine on this world is different from the others. So there is no standard how they are built, which makes it the way how computer scientists think very difficult to develop software or to utilize it in a standardized way. Then we have to transfer data. We have to transfer data from the classical world to the quantum state, which is also not trivial. Decoherence, that means the excited particles on a quantum machine, they stay in a particular state for a very short period of time. So then they decay. And then noise, the concept of noise. That means we are talking here also about non-deterministic computing. That means you don't execute something once, you have to execute it multiple times, right? And then you get the distribution of your output. So this is also a completely different concept for a computer scientist, something that we are not very used. And many of those concepts are quite counterintuitive for a computer scientist or similar discipline, I don't know, data scientist, mathematician, right? So this is a quantum computer of Alpine Quantum Technologies in Innsbruck. And this is how it looked like a couple of years ago. This is how it looks now. That means there have been huge steps in the development of quantum machines in the last couple of years. For me, as a computer scientist working also in high-performance computing, this is something quite revolutionary, because this is the machine that you can take as it is and put into a rack of a data center. This is a standardized way how the data centers are built. It doesn't need cooling. So there have been significant steps in the development of quantum machines. And how can we use now quantum machines, let's say, in our classical world? Well, we have to integrate it with the remaining world. What we are trying to do in my group, or what we are doing in my group, we are integrating quantum machines with AGPC cluster. So this is usually how AGPC cluster is accessed. You have your terminal, you have your front-end node where you can log in, compile, you can upload your files or download your files, you can submit jobs or executables. And then there is a batch system making all the work for you, deciding, for example, that the job of this person is executed on this node, the job of this person is executed on this node, and the job of this person is executed on 3 nodes because it's much longer. And in HPC, we already have different types of accelerators, right? Certain types of jobs are executed on certain types of nodes, which might be TPUs, might be GPUs, FPGAs, and so on. The idea is now that batch system fetches certain types of workload to the quantum machine, onto the quantum processing unit. Like it should be another accelerator in your data center where specific workload can be executed. So I mean, I have also to tell you, you're never going to execute A plus B on a quantum machine. It's not meant for that, but you can execute and calculate the distance between 2 atoms. And this is also necessary for different type of applications. In particular, if you look into chemistry or medicine. What we are doing also in my group, we are creating interfaces and implementing libraries so that the schedulers from the classical machine, this is the classical AGPC machine, can semi-automatically extract the code and offload it to the quantum machine. And then once the results are there, to send it back to the classic machine, right? So we build here an integrated environment where a specific application can be jointly executed in a hybrid environment with classic and quantum machine, right? And this is a typical example for a disruptive approach in computer science. Here is then also the picture showing the colleagues from Innsbruck. So you have to also understand assembling such a quantum computer is really hard work, a physical work. So you have to assembly quantum processing unit, you have to fine tune, they have to change isotopes from calcium to barium to stay so that the excited particles stay longer in a certain state. And you can also see now these machines in action. So you can see here this ion trap machine, and the blue color is, for example, because of barium, and because the particles stay a little bit longer for a couple of, I don't know, nanoseconds in the particular state. And here you can also see how this rack is assembled, right? So you can also see how these cables and how all these pieces and parts are connected and put into a rack to be a standardized machine. What else are we doing? Well, we are now developing benchmarks of hybrid systems, means we are trying to execute applications, for example, for molecular dynamics. Molecular dynamics is a typical application that you use in science, where you monitor behavior of atoms or molecules under different circumstances. So it's used, for example, for drug development, it's used in medicine, it's used everywhere. And we have developed a benchmark with our colleagues from University of Southern California and ULI, so that the molecular dynamics application is executed on the quantum machine and on the classic machine. And we try to execute the application on the quantum machine. And our benchmark is how far are we from the classical execution, right? So we have to find means to represent this computation on the quantum machine without losing too much accuracy from the compared to the classical machine. And to do that, we run optimizers. We run classical optimizers, create a cost function that give us certain accuracy then of the application that can be executed on the machine. And on top of this, we have developed an approach to execute scientific workflows, huge scientific workflows, for example, in molecular dynamics, using integrated machines. You can see here how we block and how we distribute the workload. We have certain workload that is executed on the CPU. Then we have certain workload that is executed on the QPU, on the quantum processing units. And also here you can see, for example, classical data preprocessing and preprocessing on atom trajectories is done on the CPUs. And then we have here quantum bipartite distance matrix generator, means here we generate the distances between atoms. This is done on the quantum machine. And again, we have on the classical machine data post-processing, where we have bipartite and Euclidean distance matrices that are then used for the further processing. And this paper is fall 2024 Editor's Choice Paper of Future Generation Computer Systems, and we are now running for the Best Paper Award here. If you think, oh yeah, wow, this is so super complicated, and how can I start here? Well, I can show you here. We have a lecture which is called Hybrid Classic Quantum Systems, where we try to teach computer scientists, non-physicists, quantum systems, and we try to use tools and methods from computer science you are familiar with, right? For example, we start with the single execution model, where you have state preparation on the QPU. Then in the next step, we have the job execution model, where we have the state preparation, and then we have certain number of shots in order to prepare our state, right? And then in the next step, we have the hybrid execution model, where we use a certain optimizer to achieve certain accuracy of our computation and of the state preparation. So we try to use concepts like, I don't know, loops or something like that, or optimizer that you know as a computer scientist, in order to get familiar with quantum computing. So in case you are interested and you think, okay, this is something I want to learn, I think this might also be the right lecture for you. And I would like to summarize now what we have learned in this lecture is that we have multiple dimensions, multiple methods, and multiple actors in computational sustainability. The classical methods that we use here is the trade-off, where we have multiple dimensions, for example, accuracy, maintainability, modularity, energy consumption, where we basically try to manipulate those dimensions for the sake of sustainability. We have then the disruptive methods, for example, introduction of quantum computing, developing hybrid systems, where we execute specific operations and specific workload on quantum processing unit, which is suitable, for example, for chemistry or machine learning applications. We have still challenge of integrating hybrid systems, but we have to work on mindset and education, both in sustainability and also in hybrid systems. In sustainability, I cannot change the law. I cannot force people to use less computers or to use it in a more sustainable way, but I can educate them. I can educate the works mindset, and that's what I'm doing. What I also think that we have, or you have to move out of the comfort zone, because I think that progress in sustainability can only be done if we move out of your comfort zone. And I also think moving out of the comfort zone of computer science. Thank you very much for attending the lecture. And at the end, I would like to thank to my group. Everything what I have shown today is the effort of my group, joint effort. In different research projects and in different research areas that we are doing. And I also would like to thank all funding agencies that is supporting us financially. If you have questions, I'm now very happy to answer them.
Great. Thank you very much, Ivona, for this interesting presentation. I see at the moment we have right now no other questions in the chat. I have one regarding the interest or the development of interest from the students or also from the teenagers regarding quantum computing and sustainability. You see there a rise or?
You mean if the students, young students, are interested in quantum computing? Yes. Yes, I see a lot of interest. I was also requested to organize an excursion because they want to see a quantum computer. They just don't want to talk about it. They just don't want to talk about something they have never seen, because we computer scientists, we know how a computer looks like. We are using it every day. We know what is a laptop. You know what is a desktop computer. Many know what is a Raspberry Pi, but they want now to see a quantum computer, which I totally understand. So I see there is interest. I see there is even interest in schools. I skipped some of the slides because I was running out of the time, but I can show it now. We are organizing, for example, different outreach activities. With my colleagues, we are organizing Quantum Fall Fest, where we try also to reach out to everyone, for example, also high school students. And we had a high attendance also from high school students during our Quantum Fall Fest last year. So I see definitely here is something happening.
So we have also another question in the chat regarding what's the biggest challenge you believe we have in implementing sustainability practices?
I think from the scientific point of view, I think there are many tuning knobs, as I have shown, like disruptive methods, trade-off methods. And I think we know how to do that, scientists. I think the biggest challenge is to put it into practice, to change things, to change guidelines, to change law, to force someone. For example, what is currently happening? Many companies are realizing, okay, with large language models, we need a lot of electricity. Yeah, we don't want to jeopardize our business model. So I see in US some big tech is now building data centers directly next to the nuclear power plants. I think in Pennsylvania, one of the Amazon related companies is building a data center just in the vicinity of the nuclear power plant. And I think there are micro nuclear power plants now on the market where data centers can buy really a small nuclear reactor and install it in a data center, and you get electricity for 5 years. And then you have to throw it away. So this pressure now to have reliable electricity sources for the problems, for example, that comes now with large language models, forces us to go back to the practices that we thought are not coming back. For example, nuclear power plants, right? So there are many developments now that are questionable. And this is now not only research, it includes a lot, outreach. It includes political decision making, our responsibility as a scientist, as a citizen. So many dimensions.
Yeah. Another question from the chat.
I don't see. Oh, yeah.
If there's no other question, thank you very much, Ivona. Or second, looks like there's another one. Yeah, do you believe that these companies have a huge pressure on the governing bodies in implementing the sustainability practices?
Mm-hmm. I see the pressure now in getting reliable electricity. I think that's now the pressure. I don't see the pressure in sustainability practices yet. Maybe this is coming next. Maybe. Maybe we are not yet there. Now I think there is the pressure of getting reliable electricity in the amount that is needed. I think this is the first pressure. If they are then thinking about the sustainability, I don't know.
Yes. So we have a few minutes left. Otherwise, if there's no any question, thank you, Ivona. And
Thank you very much. Thank you very much for attending the lecture, and thank you very much for being here.
And for an outlook for next week will be the topic about sustainable blockchain. And yeah, so then I wish all a nice evening and then see you next week.
Have a nice evening. Bye.
Bye.